Let's get going. So today, last weekend I have already graded your proposal. For those, so overall I think everybody done a great job. Now we have a few students that submitted proposal. If I left comments on your Moodle, please come to me after this end of this first class. I think it's more of a formatting issue. I have a few students that submit like a Word document. 就是有那个就是 Word document. So I specifically asked you to give me like a PDF document. So if it's a Word document, I think you want to try to avoid next time when we meet. So I think in the next 2 weeks, I will ask you to submit your references, your paper references. So I expect that also in the PDF version. Another stuff is I found on most of your proposal, I think overall done a great job, but one downside is that if I ask you to say give me a half-page proposal, right? So I really do expect like a half page. Some of you actually gave me like a 2-page of content. I know you're very diligent, but I asked you only half page. Second is, I think I already gave you a template of example. So if I ask you to give me a paragraph, it's a paragraph, and then if the title is what it's expect as a title, you give me a title. And if I ask a figure, you give me a figure. So it's really simple. So the overall thing is don't be very creative. That's something I want to, you can be very creative, but if I ask you to give me like a half-page proposal, you just give me a half-page proposal. It's just really very simple and very clear, okay? So some of you have some issue about formatting and the language barriers. So if it's the latter one of language barriers, that's totally fine if you want to submit it in Mandarin or in other words Chinese. That's totally fine. 假如你觉得写英文对你是个障碍的话，你绝对可以用中文写。But if you do write in Mandarin, you still are obligated to write in the format that I asked you. All right. So, say if I ask you to provide me your name and your school or institutions, you should really do that. Second is that about your grammar language barrier is that we have a very common that's even I also do that is Grammarly, so it's a software. You can install that, put inside your Word document. So a couple of you actually provide a very nice written document. You spend a lot of effort, I can see that, but probably 50% of you guys really need to spend a little bit more time try to write on your document, because when you write, I really spend my weekend reading each of these words and sentences, and I can see if you really put an effort or not. I mean, when you put some writing inside, I will know. So if it's like a copy, actually all of your document, each of your document I actually went screaming through AI detections and etc. But at this point right now, if you have document that's from AI, that's somewhat okay. But I know if it's from AI or not. Second is that how many times have you put on your document? Actually, I'm an old-fashioned guy. I normally print out your document and I put my suggestions and comment. I won't show you, but I will keep a record and track. So really just don't waste your time if you're not really spending effort on this document, okay? Because I'm really spending a lot of tremendous time reading this document. So I left comments on your Moodle. For those if I left comments to ask you to come and talk to me after this class, please stay after this first class. Okay, let's do that. I'm willing to spend time with you to help you, at least improve your English or writing a paper or whatever that helps you. Okay. So other stuff is we have students that are absent. Sometimes you have other due obligation, experiments and symposiums that you have to attend. So I asked my student to keep a record, video record. So say, for example, if today you cannot attend the class, that's totally fine. But one thing I would ask you is kind enough to send me an email just saying that, hey, professors, I have something that I really can't make it to the class due to health issues or other stuff that's kind of trapped in other that's totally fine. But I urge you to send me an email because it is my duty to make sure you're safe and healthy. At least this is my class. I normally should have go through attendance, but I'm just gonna give a quick pass on that. So I ask you again is that if you cannot attend this class, that's totally fine. I do a video record. I upload to YouTube channel where there's a link. So you can review that video anytime, anywhere. But if you cannot attend this class at this time, I ask you to send me an email. Okay, that's the least minimum thing I ask you to do. So kind of switching gear to get into today's class content is that we're moving to week 5. So today I will touch upon the topic of crystal interface and microstructure. So last week I invite my friend and my colleague at NTU to give you some scope of how TEM and EBSD can be operated on a microstructure. See some microstructure. So if you relate to this topic, you can send an email. He's more than happy to help you. So kind of continuing on the topic is 2 weeks ago I talked about diffusions, right? I don't believe I actually finished that topic. So and I don't believe I uploaded my notes as well. So what I'm going to do is I'm going to upload the notes this week. So if you haven't had a chance, writing, kind of pick up all these notes, I will have that notes ready for you guys. My plan for today is moving on to chapter 4. So I'm kind of following that phase transformations from Easterling and Porter and Easterling. That's the first guy who wrote this was Porter and then Easterling. So both these guys wrote this book, Phase Transformation. So right now I'm moving, switch gear to chapter 4 that I talk about crystal interface and microstructures. Next week I will do a summarize of diffusion on chapter 3, and then finish kind of the end of the chapter 4, which is crystal interface and microstructures. So today I will kind of move in and give you some idea of what this crystal interface and microstructure is. Okay, everything good? So by the way, is I kind of looked into the survey you guys done. So we have quite a varieties of students going on. Some have some idea of phase transformation already. Some have really no idea what exactly material science it is. So we have quite a figures, people around this class. But anyway, so I'm kind of going into today I'm trying to give a more easier angle of exactly crystal interface and microstructures, and we'll dive in as time progresses. All right, good. All right, so precipitation trending. You probably see this this kind of terminologies or phase diagram as time proceed. So for those that doesn't know, basically this is a phase diagram, right? You have the axis as the compositions and the y-axis as the time. And you have L that stands for liquid, alpha, beta basically is the phase structures depending how your atoms being arranged or being kind of aligned. And then you have a typical BCC or FCC structures. But in this case, we're just giving a name, alpha, beta, and then whatever the next phase that comes is gamma, right? So it's just according to these terminologies. So I think this phase, the reason why I'm showing this phase diagram is, I don't know if you noticed, is that one of the things is that when you see this, it doesn't really give you a picture of time, right? There's no time evolution whatsoever, right? But when you do experiment, there's always time, right? Time matters, right? Whenever you do this and do that, the time interval actually do affect your microstructures. I don't know if you ever realize that. So a great example is heat treatment, like annealings, quenching. These are time intervals, right? And with that really influence your microstructure. So precipitation strengthening, a great example that you often use as a sample is like aluminum copper, right, or aluminum alloy. So these materials is that when you quench it and then raise to a certain temperature, you get precipitate, or if you decided to kind of go and then kind of quench it down to the alpha beta phase, you will have precipitate or beta. And then things get a little bit crazy or interesting depending on your enthusiastic or passionate is that these precipitate actually you can control them, right? So if you stay long enough, it is aging, right? And then if you still maintain at this temperatures, it will be an overaging. And if it's overaging, it will be a catastrophic on your mechanical properties, right? So normally, the quickest way as a material scientist is that if you don't have a bulk material, and you really want to know what is going on through your, these kind of treatment process, how is that correlate with your mechanical properties? What do? You do a hardness test, right? So when you do these all kind of treatments or process change, you don't have the time to look at microstructures. You just go to do some hardness test. So 你去做印度来去看它说，哎 what's really going on, right? So it's the quickest, kind of evaluations of what has going on in your, during your processes. Okay, does that make sense to you guys? So for those like, undergrad students, you guys took material science before, right? One material engineering. Yeah, good. Okay. So we have this little precipitate that's actually the beta phase, and the matrix is the alpha phase, right? You guys know that very clearly, right? Good. So these precipitate is beta. So if you have pencil, you can draw. So these are beta phase, and then this matrix, 这是母基材, is the alpha phase, right? So if you're able to control, this doesn't give you time, but if you control the time long enough, actually these precipitates, these little small little dots, they actually start growing, right? So by the time of the evolutions, if it overgrow enough, it actually decrease your strength rather than increase your strength, right? So if it grow long enough, the material actually get brittle. 它变比较脆嘛，因为 this precipitate actually doesn't help to promote the movement of this location. So what we're looking over here, this is a microscopic image, so you can't really see the dislocation in a nano scale. 你看不到插排，但是如果你看这些吸触的作用到底是要干嘛？这是主要阻止插排的移动 ，right? So in one kind of quick overview, what I'm trying to kind of give you a sense is this phase diagram doesn't really give you time, right? So as we kind of move on, I'll talk a little bit how we can use time as our weapon to control the material, properties. All right. Okay, so kind of continue on the topic is that if we enlarge the microscopic images on the right-hand side, what you see is that we have these little precipitates, or what we so-called nuclei. So if everything goes well, and when I say everything goes well, is that we have these nuclei, and according to these atoms, when we cool it down over the melting temperature, it starts forming solid. So these nuclei normally do, because the lowest sulfur energies, we normally form spherical shape because it just has the lowest, surface energies. So if everything goes well, we get these little small nuclei, and with time, these nuclei actually grow. All right. Now another thing is that this doesn't also encounter how much undercooling. So once we pass the melting point, right? Say I'm giving arbitrary temperature. So aluminum that has a 600 Celsius of melting temperature, right? So if we cool down to 200, it turns into solid, right? No question so far. But if we cool down to say 400, so the difference between 200 and 400, they all turn into solid for sure. But the only difference is that these nuclei that was nuclei on these matrix, these spherical structures that we have actually is very different. So some of them can do because the undercooling that you underwent has a bigger spherical structures, while some has actually smaller spherical structures. Does that make sense to you guys? So I think in the material science book that we use is that in a lot of industrial applications, when we want to get some precipitate, normally the way they do is that they don't really kind of switch back to what you do. Is that, hey, if I want to get an alpha plus a beta phase, we normally in industrial applications, they don't just cool down to over here. It's just very difficult to control. The way they do is that they quickly quench to room temperature and then slowly raise to the desired temperature what they want for the final microstructures. Okay? So this is something I want to kind of add up. I don't think in the material engineering book they really talk about that. All right, so this is like, all right, so we have these, the nuclei or precipitate diagram. So another thing you want to take note on is that these small precipitates. So later on I'll touch upon the topic of homogenized nucleation, right? Nucleation, there's homogenized nucleations and heterogeneous nucleation, right? So for the homogenized nucleations, you can see these are just on the matrix that's growing as a spherical precipitate, right? So it's homogenized nucleation. For those that grows on a grain boundary, so what is a grain boundary? Basically, it's a misalignment between the atoms when they align. So I can say, for example, in a real application in this class right room, we have a clear grain boundary over here, right? So a very clear grain boundary because due to the atoms alignment, over here you have a line over here, and then you have orientation here. This is the grain boundary. So these defects actually provide the energies for nucleation to grow. So it has a low energy, trend to allow to grow. The required energy to grow precipitate is a lot lower for precipitate that grows on a typical matrix. So you have these that start growing. Okay, I think that's what I just want to add on. All right, so few things I want to talk about. So processes, forging. So just the reason why I'm talking about is I want to also give you about other related topic. How would that relate to the crystal structures, right? So forging in Chinese basically is 锻造. Okay, you guys know that, right? 锻造. Okay, so forging, and then casting. So what is casting? Casting is 铸造. So the difference between forging and casting, basically you're melting a aluminum and then you're pouring into a mold, right? So that's casting, 铸造. What is forging? 锻造 is, you can think about you're hitting a hammer and then you're like hitting on it, so that's forging, right? You actually be surprised, like this is, a lot of people just doesn't know the terminology differences, so I think you guys should try to remember that. So forging, over here, this is a very common process. You have a slug. So slug meaning that you just have a raw material, you extrude it to the shape, and then common thing in forging is that you have stamping, right? So stamping is like you have one at the bottom of like a fixture, and then you have another fixture, and then you put the specimen inside, and then you start clamping, right? So that's what we call stamping. So stamping is another terminology for forging as well. Okay? So I mentioned also casting is you melt the aluminum or melt the metals and then pour into a mold. So it needs to, the metals needs to be melted into a liquid form so that you're able to pour it into the mold. Okay? So 一个是锻造，一个是铸造。很多同小都会把这个搞混，我不知道，也是我不知道你们会不会搞混。All right, so another type of technologies. 3 weeks ago, Dr. Q mentioned it about metal injection molding, right? So here is a common kind of schematic I'm showing. So it's a powder-shaped metal injection molding, and the shrinkage is driven by the surface area reduction and applied pressure. So 那个驱动力，或是 I think the trend that allowed to kind of shrink down is because of the surface area reduction and the applied pressure. Normally, when you do injection molding, you have the powder that's kind of poured into a mold, and then it's pressured into the desired specimen, right? All right. So these are metal. Right. Okay. So another thing being talked a lot is centers, right? So when we do ceramic Metals you don't do centering. So ceramic you do centering is a reduction. So highlight this is a reduction in interfacial energy by particle fusing together to go below layer melting temperature. So the bottom line is that we want to reduce the interfacial energies. These layers, right? So eventually, turns to a parking structure. All right. Reduce the interfacial energies. Okay. Okay, good. So I want to continue to give you some examples. So local shrinkage, like the local, the microstructures, is associated with the reductions in the interfacial energy. So on my next slide, I'll define what is interfacial energy. So overall, the microscopic shrinkage of the body. So in my lab, we do a lot of AF, right? So these green body is before we do any debinding or centering. It's just some powders with some binders that's kind of linked together. So, and after center body, meaning it's already a final product, you can see. So it's a circular bar strip, a tube, and then some fixture via design. Right? And then on the right hand side is another great example of green body, center body. So this is a mullite structure. So it's an aluminum oxide plus silicon oxide. So yeah, so fancy about doing AMs is that you don't need to have a mold to form the structure, right? You can print whatever desired structure you would like to print, right? So this is a lattice structure of a 5-inch tall of a lattice structure. Okay? All right, so we've been talking a lot about interfacial, right? So what is interface? We're gonna have crazy writing notes right now. So interface, 界面, interface. So we're gonna define that liquid plus vapor, right? And solid plus vapor. And then solid. Okay. So an example of liquid vapor is, for example, a drop of water. And solid to solid example. So solid vapor is, let me give you an example, is that if you have a microstructure and then you have porosity inside, right? E-O-R-O-S-I-T-Y. So this is a microstructure. 就你的显微组织里面，然后有洞洞在里面嘛，洞。So that's porosity vapor, right? So solid to solid over here. What's the example of this very value? Second example for solid is interface composition plus the boundary. So in solid-solid interface, you have two scenarios. One is that you have a grain boundary, right? As I explained, grain boundary. Same composition, but it's just across the interface. So it's atomic misalignment, right? Second is interfaces when the composition across the boundary is completely different. So you just have two different compositions that occur, and you also have boundaries that fall. So it's just, again, solid. So think about like, say, I'm just arbitrarily giving you an example like copper to iron, right? So these two, if you try to weld it together, there's like boundaries, right? So it's a solid to solid, right? So that's I'm just arbitrary. I don't even know if they do copper to iron. Maybe they do. Two different, completely different metals. Okay? All right, could you guys copy this down? So later I'll talk about surface energy. Why surface energy or interfacial energy is important. Okay?那个就是因为我们这毕竟是那个本级的学生比较多，但是因为这门课是EMI嘛，那我会是这样的，我会尽量就是在周末前我就会把讲义上传上去。是这样，就是我上课基本上会大量抄笔记啊，所以你有几个方法避免你睡着。要么就是先把这个讲义下载，然后我上课抄笔记抄；又或者呢，就是你拿电子版也是抄也可以，不是要纸本都可以。那如果就是你怕你会睡着的话，那你就尽量想办法不要让自己睡着，好不好？你就大量上笔记，这个是一定要传授的知识。我总不可能每天在上课就是唱啊跳啊去取悦大家，好不好？这是很基本的东西，要讲还是要讲，好不好 ？OK？ Gina, you okay? You good? All right, good. OK， 你看得懂那个我写的英文吗 ？OK 吗 ？OK。All right. So if you have not finished, that's okay. I will upload this later, end of today or maybe for tomorrow. So I want to define what surface energy or interfacial energy is. So surface energy 面的话 per unit area is gamma. 所以是 surface， 这个是伽马，不是 R 哦，你不要写错伽马。Okay, so the unit is joules per meter squared. So surface free energy here we define subscript S, right? So it's free energy, G, and then S is just surface free energy, okay? So GS equals to gamma times the surface area, area. So you can see so the surface energy is just joule, right? So if you move the surface area down to the denominator, 就分母的话 you get gamma, right? So the gamma, the unit is joules per meter squared. So this unit is joule, okay? Area is just the area. It's very simple to understand. So how do we, come up with this equation? So I want to elaborate a little bit more. Let's use slope bubble, for example. So this is this example. So imagine that you have on a wall and you're able to build up a small bubble. And this radius is R, right? And then somehow you start blowing the layer gets a little bit larger, right? So this over here is ER, like a small amount of radius that's increases, right? So we can find that as GS equals to gamma and then 2 pi R squared. So this is just a half of the boundary. Okay. So that's the entire area of the cap of the bubble, right? So if we do a derivative of a boundary, you get a 2 pi R squared, okay? So for increasing the bubble of ER, the smaller the GS equals to gamma 4 pi R ER. And the surface area is 2 pi R squared. So the smaller part of EAS is 4 pi R. So if we do a derivative for EGS divided by EAS, all I'm doing right now is gamma equals 4 pi R ER divided by 4 pi R ER. Okay, gamma. Okay, so this is a material property. All right. So the surface area is this half cap of the bubble, right? So that's the area, it's 2 pi R squared, right? So if I take a small portion of it, we do a derivative, right? So you get 4 pi R ER, right? So the bubble is continue to increase. So DGS divided by DAS is gamma 4 pi R ER divided by 4 pi R ER, you get gamma. So that's, actually this is a material property. So I just wanna kind of let you know how we get gamma. So that's a fixed property. It doesn't change with time. Right? It's a material property like Young's module. Right? So it's also an intrinsic property, right? Like density as well. Right? So this is, if you have no understanding how I do my derivation, my derivative, just remember gamma is a material property. Okay? All right. Any questions? So I don't know, some of you, I don't know if you, in your experiment, you encounter powders, or at least in my lab, we do a lot of powders, right? And then you have all different sizes of powders, right? You have like 1 millimeter, big pot of particle size, and it goes smaller to nanometer size. So one thing I would say about dealing with powder is that sometimes when I walk, along the hallways, I would, maybe not in this lab, in other people's lab, if you're dealing with powders, I strongly suggest you really have to wear a mask. Like that really help you for your health and hygiene, regardless how big the powder size is. So normally, if it's dealing with nanoparticle size, I would imagine it's in a aqueous solution. So it's in a liquid solutions. Is that you seldom see nanoparticles as a solid itself in like a container package. There is. Now, if that it is, normally it's contained inside like a gas box, like a box, like a gas box. Otherwise, if it's in a micrometer size or larger size, is that it's like cold or safe in a container. But regardless, like again, how big the size is, I strongly recommend you should wear a lab coat and gloves and all the gear protections, because I actually, I study over here, and then I got my PhD in, abroad, and I was taking this hygiene test, and those science, like the hygiene safety officers, explain the detrimental of inhaling these powder into the lung. Right? So again, when you inhale stuff, your body doesn't tell you if you're inhaling the powder or not, right? Regardless how big, even the powder is big enough that it conquers the gravity, at a certain point the powder still flies into this normal atmosphere. You're able somehow to suck it into your lung. So once it's inside your lung, there's no way to get it out. All right, just FYI. So I see a lot of, I don't know my students, but if you're dealing with powders, it's best you wear a mask. Now, in terms of mask, the funny thing is that the people that wear masks, they usually use these, for those for you feel sick, you wear those kind of masks. So there's different masks. There's masks typically for powders masks, right? That help you filter powder. And the interesting is these masks also have different ranges. Like some they're particularly for certain range of powders as well. Second is that my senior colleagues or my former colleague always explain that powders never assume that it won't explode, regardless it's metal or aluminum. Even aluminum powders, if it's small enough, explode as well. If you have powders inside a closed room and then it's flying, it will explode, I guarantee you. So a lot of a great example is that when you see powder that's getting ignited, fire, one of the instincts is to get a fire extinguisher with water and spray it out and hoping that it will kind of die away. That's a false narrative. Some powders, when you at that point where it starts ignite and then you spray with waters, actually just help again to ignite and then have a bigger blast, regardless of what place of you that ignite that powder. So is powder very dangerous? Yes, it is very dangerous. Kind of use it with protection skills if they're necessary as well. Okay? So don't, when you see powder, just don't think that it's just powder. No, it's really not. Okay. All right. So I mentioned about all different kind of powder, right? So I'm gonna do some kind of exercise. So say, for example, we have big powder and small powder, right? 1 and 2. So which, this is a very simple question. Which has a bigger surface? Which has a bigger surface? 1, right? One is very. But the thing is, why the reason I'm using this example is we're really comparing with orange and apple, because in terms of centering, you do know the smaller particles is a lot to do your centering to get a compact structure rather than big particle, right? Because of surface energy, right? Because smaller particles has a larger surface area compared to bigger particles, right? So this kind of exercise I want to go through is just to kind of help you emphasize that idea a little bit more. So let's compare surface area of R equals to 1 micrometer. So 1 micrometer is on the left hand side versus R is 0.1 micrometer. So these are all spherical. I'm using spherical particles. Right, so the area, if you calculate that, for the 1 micrometer is 4 pi other one, area, 0.1 micrometer is 4 pi. So it's a lot smaller, right? In terms of the area, right? So if you compare these two, the area of 1 micrometer is 100 times greater than 0.1 particle, right? So it's 100 times greater, all right? Just doing a very simple comparison. All right, so this is the area one, right? So let's do the value. So if it's the value, so dg is 1 micrometer. So we got a 4 pi r cubit, you get 4.2 times 10 to the power 18. And if it's 0.1 micrometer, you get 4.2 times 10 to the minus 21. So conclusion is, if you compare these two, we need 100 times small particles to equal the value of a large particle. Okay? So for the area, it's 100 times greater. Compare number 1 and number 2. In terms of the value, the number 1 is approximately 1,000 times bigger to the equal value of 2 compared to 1. All right? Does that make sense? I'm just putting numbers inside, right? So like kind of explained, if you compare big and small, if you compare these two particles, it's not really on a same standard. 没有在同个基准点去比，对不对？ So if let me increase number 2 particle. So if we have the same mass or value for number 1 and 2, the 0.1 micrometer particle will have 10x of the surface area of large particle, right? So if you increase number 2 particles to equivalent amount of number 1 particle, actually the surface area for number 2 particle will be 10x the time of number 1, right? So if you still recall on the previous slide, I talked about surface energy. The surface energy is defined by what? By timing the area, right? So the larger area means that you have a larger surface energy, and with larger surface energy, meaning that it has the energy to kind of, do its centering, compact, and close up the porosity, right? So why am I trying to talk about this is normally when we do measurement of surface area of particles, we don't report the surface, we report the specific surface area. So the specific area basically you include the value terminology inside, and with that, then it doesn't matter today how big the particle size is. All right, so I'm gonna you guys, let me wait for it. So, so the specific surface area is basically a define of the surface area of the particles divided by its value and density, right? And with that value, it doesn't matter, with that reported value, then you can compare with any of the particles that you do your measurements on the same standard, all right? So that's important. If you're doing powder, you should use BET. So BET is the device where you measure the specific surface area, and with the specific surface area, then you can correlate what is your energy that required to have a compact centering structure, all right? So it's, at the end of the day, this isn't really about, hey, how many small particles or how small of a particle it is, right? It's about the surface area, right? So right now, I'm just assuming it's all spherical particles, right? So it depending on the orientations and the directions of the microstructure. So later on the slide, I'll also talk about that. All right, so any questions so far? 有没有什么问题？ So I think another stuff I want to kind of share is, you know, powder is actually important. I don't know how although I'm teaching phase transformations, my next semester I will have powder metallurgy. Supposedly it's offered next semester, but I'm offering a little bit early next semester. So I don't want to limit your imagination about powder because, you know, powder can actually be also used in semiconductor environment. So I don't know if you know, in semiconductors we do a lot of polishing for wafers, right? So polishing wafers actually you need a slurry that consists of a solution plus aluminum oxide as well. So powder, for example. Daily common good for cosmetic. I don't know if you have a girlfriend or wife. Those cosmetic actually use powders, titanium oxide as well, for sunscreen or your face, you know, things. That's also powder as well. There's a lot of stuff you also use powders, the powder coatings for your cars, aeronautic, electronic device, everything, right? So there's a lot. So I don't want to limit saying that powder is only traditional manufacturing. Actually, it's a high tech. Good. So I'm gonna move on to those. So Pacific areas is so assuming again we're just spherical, right? So it's 4 pi all squared, right? Divided by the value times the density. Okay, so this is density. So if you do some quick math, you get 3 out of all times dou, right? So the unit again is grams per meter squared, right? So what this tells you is that if you have a smaller radius of particles, the density is always fixed, right? So if the density is fixed, if you have a smaller radius of particles, basically you have a bigger amount of specific surface area, okay? So smaller R, you have bigger SSA, right? Right? So, question is, what happens if your powder is not spherical? So, how do you encounter? So normally, with this, you not spherical, you actually times a factor. Okay? So, which I'll talk about that in my following slide. So, factor meaning that closer to 1 might be sphericals, and then lesser than 1 is non-spherical, right? So you time a factor, right, to compromise non-spherical. All right, so good. Let's have a short break. For those I left comment on your Moodle, please come and talk to me. Well, let's have a break and then we'll come back on the next session.